Hello and welcome to this lecture 10 of applied ergonomics. We were talking about manual systems in the last lecture, particularly manual systems related to work study, where there is the involvement from manual subjects and also hand tools. So, basically the power that goes into any operation comes from a human subject. That is how you interpret the manual systems. We also talked about briefly about various other systems like man machine systems as well as fully automated systems, although we did not delve into the details of it. So, this particular lecture is intended to give you an idea of what we mean when we talk about man machine systems or automated systems, what are the different associated paraphernalia associated with these systems. So, let us look at what we mean by a worker machine system or a man machine system. So, as from earlier definition, it is quite clear that if you are using powered equipments where there is a scope of doing on own by the equipment concerned, it is considered to be a worker machine system. So, of course, the role of a worker there is completely related to loading, unloading, changing the different conditions of machining or even the tools from time to time, and the support system that in general needs to be done for an interrupted operation sequence on the machine is being provided by the worker. So, he is a very important component in such complex systems, but once the loading and unloading has been done and the basic operation is to be performed, the power does not come by the human subject, but from the machine itself, and power could come, for example, in a transfer press which is mechanical from a big motor, or for example, hydraulic on a big set of cylinders with different oil and other pneumatic circuitry associated, oil circuitry associated. So, these are classified into worker machine system. Some examples could be machinist operating a milling machine. Once the milling machine has been set up, the indexing has been done, the arbor as well as the tooling as well as the workpiece is mounted. Now, it is left after switch on button, it is left onto the motor of the milling machine to perform the power addition to the machine and drive the various stages in sequence, so that there can be gear cutting or something, some operation which can happen or it is intended to happen. Similarly, is the plight of a construction worker operating on a backhoe or a truck driver driving a 18-wheeler. So, basically all the power that is needed to carry the load, push the vehicle is done by the engine, but the control on the engine rests on the truck driver, who basically is the worker for such a worker machine system. There could be other examples like worker crew operating on a rolling mill, or a clerical worker entering data into a PC. So, all the data entry steps and preservation into memory, both random access memory and read only memory, are done by the PC through a powered mode, but the clerical worker is helpful for just inserting relevant data. So, all the computation, the processing is done by the processor. So, these are examples from daily life of worker machine systems. Now, there are different relative strengths and weaknesses that any system does have. In case of strengths for humans, there are various strength components which we might consider. For example, human subjects can sense unexpected stimuli, can respond to such changes in stimuli. They can also solve problems quickly, cope with abstract problems through knowledge as well as intuition, adapt to change. For example, there is a sudden change condition, there is a quick adaptability, generalized from observations. Okay, so, if you have experiential observation, then that is the best part which a person can use, knowledge domain from his previous work sphere and as applied to the current work sphere for any changing situation or a problem which emerges. So, these are some of the relative strengths. Also make decisions on incomplete data. So, these are some strengths related with the human subjects. However, when we talk about strengths related to the machines, the biggest strength that the machines would have is that they perform repetitive operations consistently. There is a powered mode, there is a distribution of power, and all it needs is to set up the power in a particular manner, so that there is repetition of tasks undertaken by the machine. It can store large amounts of information. So, there is the capability nowadays of both storing as well as processing where you can retrieve the data from the memory reliably, apply high forces and power based on some of the data which comes, and make routine decisions quickly. So these are some very important strengths that machines would have. And so basically the idea behind designing the worker machine system is to combine the relative strengths of each with respect to one another, so that there can be a correct mapping, okay, in that sense. So when we talk about different powered equipments, there are different power equipments available based on whether they are portable or mobile or stationary. So for example, let us look at portable power drills, chainsaws, electric hedge trimmers. These are some equipments which are power tools. They are actually either having a wired orientation or even a battery operated orientation, or in some cases, for example, when we talk about chainsaws, etc., there can also be or electric hedge trimmers. There can also be engines associated with such tools. So there is some source which emanates the power, and it's mobile, okay, or it's portable, not mobile really, but portable, okay. So basically you can lift from one place to another, and you can do different operations through that such kind of tools. There are mobile power tools where there is a certain mobility, like for example an engine mounted on the top of a chassis moving ahead, okay, for example in case of forklift trucks, for example, or let us say generators which are transported to the construction site to generate electric power. Transportation equipment as such, all cars, buses, trucks, all railway systems, railway engines, they are all associated with a power unit which is in form of an engine, or which it's in form of a generator, even sometimes gas turbines smaller in size, which would actually be able to go from one place to another through in a chassis driven carriage, okay. So those are mobile powered equipments. So these equipments are typically used in a lot of heavy industry work. Then there are stationary powered machines. For example, there are machine tools, lathe, milling, where there is need and necessity of somehow preventing vibration by creating a firm base and then grouting the machine to a certain area. So it makes the equipment completely stationary at a certain place. You have office equipment, cash registers, heat treatment furnaces, where if you station it at a place, generally it's not advisable to move it out of that place. So these are sort of powered equipments in various industrial and other work machine systems, which have different types based on how they perform, what they are supposedly performing. It's sort of a classification into the different types of how they can be carried out or carried over, or how power can be applied. So there can also be differences in terms of the numbers of workers and the number of machines associated with each other. For example, there can be a case of one worker, one machine. Let us look at the example of a taxi cab driver and taxi. Okay, so this is something which is talking about the taxi being the machine and the taxi cab driver being the worker itself. So there is exactly one person controlling one machine. There can be a case where one worker controls multiple machines. For example, sometimes there may be more than one machines in a machine cluster. Okay, so let us say we are talking about an automotive engine shop, and there are multiple machining centers on this engine shop. Typically they are done on a S-type layout, on a U-type layout, where there are machines and inspection stations in between, and such machining clusters are also referred to commonly as transfer lines, where there is a entry of the object or the workpiece to be machined from one side, and it goes through roller conveyors as it goes to the different machining stations, where there is a continuous loading, unloading, and also inspection carried out. So in such kind of systems, there may be multiple machining centers all running on CNC capabilities or processes which are fairly automatic in nature, but then there are certain operators who are involved in loading the workpiece, checking the workpiece for its initial let us say cylinder, the finish of the cylinder liner, etc., and then later on as the equipment or later on as the unit, the work unit moves ahead, it completely goes to the machine domain and then comes out back, again when the operator can finally inspect and take back and carry it or load it to another container. So this is one worker, multiple machines kind of situations. There can be also a case of multiple workers, one machine. For example, let's say when we talk about running a big transportation unit like a ship, or for example an airplane, or even like a train, there are going to be multiple stakeholders who will be associated with running this. For example, typically an airplane has a pilot and a co-pilot, so there are more than one workers for this one machine to carry ahead. Or even in railway engines, or in railway in trains, there may be 3-4 operators, 2 of them on the engine side, 1 on the signaling side, and so there is a way that they communicate with each other and run this whole system. So that's again an example of multiple workers, one machine. There can also be a case of multiple workers, multiple machines. For example, when we talk about emergency repair crew responding to machine breakdowns, it is possible that you have to remove the problem, or you have to start the facility in a relatively shorter amount of time, and it may be worthwhile to put more than one skilled people on the job who can actually go to multiple work centers and who can take corrective actions or measures so that quickly the system can be revamped, okay, or set initially back to 0 conditions so that it can operate. So this is a case where you have multiple workers and multiple machines. So there are numerous such examples where the number of workers and machines could vary with respect to one another when we talk about worker machine system design. So then we talk about the level of operator attention which is involved in such systems. So for example, there can be cases where the operator who is involved in performing on the work machine system may have to give attention for full amount of time that is involved with the machine. Let us talk about a case of welder or welding operation performed by arc welding. So the arc is generated whenever the operator itself, the operator concerned, is basically able to take the carbon electrode very near, take the electrode, welding electrode very near the workpiece, and then suddenly shift back so that there is an arc created. Now once the arc is created, then it is completely in the operator's control, and the gap needs to be maintained so that there is on one side molten flow of material where the electrode size reduces, and the gap needs to be continuously changed, or gap needs to be continuously maintained by the worker by moving the melting electrode nearer and nearer to the workpiece, so that you can ensure that the arc sustains itself. Okay, so these kind of operations does involve almost full time attention for the concerned person working on the system. Or if I talk about, let's say, a slightly automated mode where we are talking about let's say tungsten inert gas welding or some other process where there is a feedstock which is actually giving a wire electrode and feeding it out away from the nozzle, but still there is always a tendency of the unless it is fully automatic machine, there is a tendency of the worker to actually guide the nozzle into the area where welding has to be executed. So therefore there is always a full scale attention of this worker till and until the welding process, the actual process of molten metal reflowing into or flowing into the gap and joining to, let's say, parent metals, that process continues. So these are all processes which would seek full time attention. There are also part time attention during each work cycle kind of systems. For example, I talked to you about a machine shop where the only work that could be done, let's say we are talking about a CNC machine, so only work which could be performed by a worker unless there is some in between intervention needed because of programming error or some other issue during the cycle. So it is at the beginning of the cycle and end of the cycle. Okay, and the beginning of the cycle typically has work components like loading, unloading, even change of tooling, inspection of tooling, so on and so forth, and then towards the end of the cycle again these issues are revisited so that the next cycle can be started. So in that kind of a setup, you don't need to continuously attend to the machine once you have loaded, unloaded the sample, and then also checked about the tooling systems, etc. And you have also seen that all the zero setting is being done, all the let's say backlash errors, etc. have been removed. Then you leave it onto the machine and let the work cycle continue on its own. So during the time the work cycle is continuing, even if you don't attend to the machine, is going to do its job properly. So therefore, you need only part-time attention during each work cycle in such cases. So we say that worker loading and unloading a production machine in a semi-automatic cycle could be such an example. There can be other cases where the level of attention could be periodic with regular servicing. For example, when we operate a crane, okay, in a steel mill, you need to be also very careful about probably at every shift end seeing all the joints and all the cables and inspecting the different, let us say, components associated with the crane for snap and breakage and also fatigue, so that you do not have any accidents in the next cycle of operation. So there is a preventive maintenance which is needed probably at the end of every shift or end of every, let us say, work cycle period sometimes, because you need to make sure that the object after surfacing is safe enough for the next cycle, okay, or it can get carried away in the next cycle without much of a problem. So so such attention systems or such systems can be referred to as systems where the worker is periodically attending to the concerned problem. And then there could be another kind of system where there is periodic attention with random servicing. For example, there could be firefighters responding to alarms. So these are some issues where the alarm can only be set in when there is one in a kind of incident of a smoke or a fire coming out of a building, and in order to show the emergency preparedness, there are also fire drills from time to time where the alarm is set off intentionally to see how prepared the team is to address the issue. So but then in this particular case the attention falls in a periodic manner, but on a random basis the demand comes up for such service or such attention. And so you have to be prepared, you have to have a wing of your organization which is already prepared to meet any such kind of emergency level operation. So these are the different levels of operator attentions that one could possibly think of when designing the worker machine system. We can then look at cycle time analysis for such systems. We have done the same in case of manual systems. So in case of worker machine systems, we also have a scope for analyzing how much time would be needed to execute a particular operation on such worker machine system. So there are typically two categories in terms of cycle time analysis of such systems, or what kind of cycle time is related to those systems in which machine time depends on operator control. In fact, if I looked at a power saw being operated, or a, let us say, power saw used for cutting the lumber by a carpenter, or in fact, let us say when we are talking about digging drills for concrete, etc., where a section of the road is being excavated. So in these kind of situations, whenever the operator initiates the work, the machine is merely an aid to give a power factor to his work. And in those systems, you can say that the machine time totally depends on the operator control. If today if we have a operator who is actually let us say working for at 50% efficiency throughout a shift of about 4 hours, it means that if he has been allocated to such a work center where his operation is dependent on how much can be done really with the power tool that he uses as an aid. So in that event, the efficiency of the machine, even though there is a capital investment, will fall down. So typically when you do job alignments, you have to look at the efficiency of individuals, and those people who are more efficient to a job will typically be aligned to machines which are where the cycle time depends on the worker itself. Okay, so you are using the powered tool for all times to get more amount of work done. That is the whole idea while doing a work system design for worker machine kind of systems. So the cycle time analysis is same as manual work cycle, because obviously whenever the effort is being done by the human being, the power, although coming from a machine, does not make much of a difference of the time. So the amount of time that the human being does effort in terms of, let us say, thinking or pressing buttons or somehow controlling a machine would typically be the work that is being rendered by the machine itself. There is no additional work done by the machine when it comes to finding out the total working time. Now, there may be yet another class of machines where machine time is constant and independent of operator control. For example, let us say a system which is semi automatic. For example, we were talking about this transfer lines for machine shops which has a cluster of CNC machines. So, here the loading unloading time is quote unquote the time which the operator needs. Apart from that, whatever is being done is being carried out by a machine with a machine cycle time. So, once the machine has been loaded and it has been powered on, then really everything is out of control of the operator and in control of the processor. And so, in such cases also the cycle time of the machine depends on the program or in the control, the level of control that is there in the machine rather than on the operator. But there is a small component of the operator contributing in terms of loading unloading, which shifts that start point ahead in time and which may lead to an overall extension in the work cycle time. So, there we have to also see how much delay is being done by the operator for actually the productive cycle of the machine to sort of maneuver all portions of the working time cycle in totality. So, such analysis has to be carried out in terms of classifying systems into where it depends totally on operator what is the machining time, and in system 2 where it depends on the machine, but subjected to the fact when the operator starts the machine. Okay, so that is how you analyze for cycle times in these work machine systems. So, so there is typically no overlap between worker and machine. Typically work elements and machine elements are sort of, worker elements and machine elements are sequential in nature. For example, when the worker is busy, the machine is idle and vice versa. So, therefore, while studying or while let us say demarcating into different elements of work, it is important for one to estimate what is the total amount of time spent by the worker for the cycle to operate and the machine time in unison. So, in such a case the normal time of the cycle, the work cycle, can be referred to as the time which is needed for the worker to perform normally, where he initiates the machine or starts the machine plus the machine time. Okay. So, these are added together in sequence for estimating the normal time. So, in this particular case, if we wanted to compute the standard time would really be related to the normal time of a worker times the allowance factor here due to various issues like delays or the performance or fatigue kind of factors. And I think we have extensively discussed this while doing manual work systems as well as work systems in general. And then there is a similar kind of idle time related to machining, because obviously there are certain slacks in time which you can't avoid. For example, slack involved in collocating something to the origin or resetting back the machine. There is a stage movement which happens from the existing position, particularly in CNC based controls, from the existing position that the machine is in to the position which is called reference 0. Okay. So, these kind of motions are out of control and these kind of motions do consume time, and so therefore, there has to be an allowance factor for calculating the even machining time with such kind of machining based idle components which are necessary evils. So, therefore, the standard time of the cycle now is obtained through this particular formulation here, which talks about the normal time of the worker plus times of A1 plus APFD plus the total time that the machine would be operating, or the cycle time of the machine times of 1 plus idle time, or let us say the allowance factor given to the machine. So, this is how you calculate the standard time for the whole work cycle. So, mind you, in the only worker or only manual system, this was completely dependent on the worker, and so this component was 0 or missing in this particular system, because there is a sequence which is followed where the worker first works and then the machine starts operating. So, therefore, both the times are included for calculating the overall cycle time sequence. So, that is how you calculate the worker machine with assuming almost no overlap between the ending of one processor operation and starting of the other. So, then we can classify work elements into internal and external types, generally it is probably a prudent idea to make work, more and more work elements of the internal type, and let's look at what they are. So some of the worker elements are performed while the machine is working. So you can say that the internal work elements are performed simultaneously with the machine cycle, and the external work elements are where work is performed outside the machining cycle. Okay, so now if the machining cycle includes loading, unloading and the operation time, something like rework, okay, which may come because of inappropriate machining, could be considered as the external work element, because it's outside the cycle time. It's happened one in a basis, let's say in 1 in 100 cases or something, where you need reworking because probably a tooling got damaged in that particular machine cycle or something happened, and it's quite random. It's not that it will prop up in every cycle. Okay, so in such kind of cases, these are the external work elements which are out of the machining cycle, which otherwise includes only the loading, unloading, the inspection and the machining time. So we must in our whole design agenda try to put more emphasis on as much as internal work elements and reduce as much as external work elements from a system. So if we can avoid non-compliances where there are sudden prop-ups of work elements which are outside the cycle and which are undesirable, they should be avoided as much as possible. That is the whole idea behind designing. So when you are trying to look at work elements, and you know, it's always prudent for you to generate as much as internal work elements. Probably you take some more inspection measures within the machining operation so that such kind of non-compliances seldom occur, or their percentage reduces more. Maybe they become in ppm. Okay, so try to avoid the external work elements which will be performed sequentially with the machine cycle, so while designing the work cycle. So now I think we'll focus a little more on automated work systems and what do we mean by this terminology. So far we have looked at manual systems and manual or machine work systems, but we have not really looked at cases where everything is controlled by a set of robots or a set of machines which are there on the line. For example, when we talk about PCB assemblies, or let's say electronic assemblies for different components like handycams or video cameras, or let's say even record players or CD players. So we are looking at assembly lines which are completely operated through a set of robots, and there is hardly any human intervention there. So such kind of a work system where automation as a technology is used by which a process or a procedure is accomplished without any human assistance is known as an automated work system. Okay, so an automated work system typically would then be implemented using a program of instructions which are timed in a way, and they're combined with a control system that executes such instructions in a proper manner, in a and things related to cycle time, etc., are predefined in the program. So what you are trying to establish is to standardize everything in terms of what you lay out in terms of such program codes, and now it all remains as to how the controller interprets it and implements it, and how fast it is or rapid it is. And there you have very less possibility of slack because all controllers are designed to operate at quite a bit of speed. So how much so it all depends on how much time the processor takes to really process the data and implement the data. And so therefore you have everything more deterministic in nature and very less chances of misoccurrence, or let's say things which will create external elements, work elements, and everything can be within the cycle or planned within the cycle or cycle time accordingly. So power is typically required to drive the process and operate such a control system. There are many examples of semi-automated and fully automated machines. For example, if I looked at the levels of automated systems, there can be semi-automatic machines which perform a portion of the work cycle under some form of program control. There is a human subject or a worker who tends the machine for rest of the cycle. For example, loading, unloading, or maybe even checking the tooling quality as well as that of the machine workpiece. Operator has to be there in every cycle, because unless his attention is there to start and stop the process won't work. And then there is a fully automated machine which operates and for extended periods of time with no human attention. Okay, so such systems are where all you need to do is to sort of press a button and everything else is taken care of by the system alone. So this particular photograph shows automatic robotic spot welding cell on an assembly line for the photo has been pulled from Ford Motor Corporation. So you can see these welding robots typically put spots. Okay, so spot welding is mostly the most common means of welding carried out in automotive assemblies. So here, for example, the robo is probably working on a machine panel or a press panel, which is a section of a car, and trying to create some spot welds between two or more sheets. And so such a system can be called fully automatic system, because once you have switched on the press button, it's pretty much out of control of your domain unless the whole cycle gets executed, okay, and the machine is ready for the next cycle. So I think we'll stop this lecture here, but in the next lecture we'll talk a little more about industrial safety, hazards, some regulatory means and measures which are available, and we will see how the factor of safety can be integrated with whatever we have said so far in terms of work system design, so that it becomes overall a reasonable level of work environment for all sides, including the human beings as well as the work system side, to work in harmony. So we'll finish this lecture as of now. Thank you very much. Thanks.